Good morning, everybody.
Good morning.
Fantastic to see so many people who want to hear about an eclipse of the sun. It might have something to do with the fact that this afternoon there's going to be an eclipse of the sun, which I'm sure you all know, otherwise you probably wouldn't be here. So this particular talk, I'll be saying a little bit about why they happen and when they happen, and I'll be recounting an experience I had 2006. It doesn't seem like 20 years ago, but yes, 20 years ago, I saw an eclipse in 2006, a total eclipse of the sun. Unfortunately, that wasn't in the UK. I had to go to foreign lands in order to see this. And the same is true of the eclipse this afternoon. From the UK, it will be partial, but I'm going to describe what it's like to see a total eclipse of the sun. And then I'll say a little bit about eclipses that are coming up, including a little bit about what's going to happen this afternoon or early this evening. So first, of course, the obligatory safety. You should not look at the sun ever, 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 unless you're wearing appropriate eclipse glasses or you're with somebody who knows exactly what they are doing rather than just second guessing. Never take any risks with your eyesight. So eclipse glasses basically are for everybody, regardless of age, and in fact, regardless of species. Everybody should be protecting their eyes. Some dogs can pull it off with a certain amount of pizzazz. Some just haven't got the ears for it and don't quite know what they're doing. But with all seriousness, make sure that you don't try and cut any corners. Make sure you've got a pair of eclipse glasses. If it's only one per family, then share them around. Don't be tempted to squint at the sun and see if you can see what's going on. The sun is very bright. Perhaps you didn't know that, but yes, the sun is very bright. It's very hot. The surface of the sun is 6,000 degrees, which is why it's such a bright disk in our skies. Rather surprisingly, the atmosphere of the sun, which you can see in this particular cartoon, it's not an actual image of the sun. Here, the outer part of the sun's atmosphere is called the corona, and that is at an amazing 2 million degrees, for reasons that we don't really understand. How come when you get further away from a hot body, it gets even hotter? That just doesn't seem to make sense. And physicists around the world are trying to understand exactly how the sun works. Despite the fact that we've been studying it for ages, we still don't understand everything about the way the sun works. But it's the fact that it's at thousands of degrees that makes it so bright, which makes it a danger to your eyes. The sun gives off an awful lot of light and heat and other particles, some of which hit the Earth, but the Earth's magnetic field protects us most of the time for what the sun is pushing out. Occasionally, some of these particles from the sun do get through, and they tend to get funneled into the North and the South Pole, and we get beautiful aurora borealis or aurora australis. These are aurora that I photographed from Iceland some years ago. Occasionally, you can get some hint of the aurora further south in UK latitudes, but the aurora is really spectacular if you get to the Arctic Circle or if you're lucky enough to go to the Antarctic Circle. Of course, the moon itself can be a fascinating object, and certain astronomers spend a lot of their time simply studying the moon and watching it from night to night as it changes phases, and you see some details in the craters or the mountain ranges as the sun angle casts shadows which allow you to see structures on the moon. But in this particular talk, we're not interested in the moon as an object to be studied. The moon is simply something that is going to block the sun. It's basically an occulting disk. So although it is interesting in its own right, not this particular talk. So let's have a think about what's actually happening. This is not to scale because the distance to the sun is huge and the sun is very much larger than the Earth and the moon. But just to give you an idea of what's happening, the shadow of the moon is long enough to just reach the Earth. It happens to be a coincidence that the size of the moon is 1/400th of the size of the sun. Or let's turn it around. The sun is 400 times bigger than the moon, but it's 400 times further away, which means the shadow of the moon is just long enough to reach the surface of the Earth if things are lined up correctly. If the Earth and the Moon and the Sun are lined up just right, then the length of the shadow is just about enough to touch the surface of the Earth. And so if you stand on the surface of the Earth at that particular point, you will see a total eclipse of the Sun. Bear in mind, the distance to the Moon isn't a fixed number. The Moon orbits the Earth in an elliptical orbit, not a circular orbit, so the distance to the Moon varies slightly. So let's just see what effect that has on eclipses. If we are at this particular point where the Moon shadow just touches the Earth, we get an eclipse which is relatively short because the Moon is only just big enough to cover the disk of the Sun. If we were a little bit closer to the Moon, or if you prefer, if the Moon was a little bit closer to us, the disk of the Moon would be larger, and hence as the Moon moves, because it's got a larger disk, because it's closer to us, then we get a longer total eclipse. And if the Earth is further away from the Moon, or if the Moon is further away from the Earth, the Moon might not be large enough as a disk in the sky to actually cover all of the Sun. And then we get a so-called annular eclipse. So what that means is, in the case of being relatively close to the Moon is larger than the Sun. As you can see, this shadow disk here is larger than the size of the Sun. And for a total eclipse that's short, if we're just at the right distance, then the size of the Sun and the size of the Moon are essentially just the same. Whereas if the Moon is a long way away from the Earth, then the size of the Moon is a little bit smaller than the size of the Sun. So we can get lots of different types of eclipse. In this case, because the Moon's disk is quite large, it's a long eclipse. As the Moon moves, it covers the Sun for quite a few minutes. If the Moon is only just the right size to cover the Sun, the eclipse will be very short. It could be only a few seconds and then it's done. And in the case of the Moon being further away from the Earth, the Moon's disk is not large enough to cover the Sun, so there will always be some Sun showing. And in mid-eclipse, you will get this annular effect, this so-called ring of fire, because the Sun will never be blocked out completely. So lots of different types of eclipse. I'll mention annular eclipses again a little later. Why don't we get eclipses every month? If the Moon goes around the Earth, and why doesn't it line up with the Sun once every month? Well, that's simply because as the Moon goes around the Earth, its orbit is inclined. It's tilted by about 5 degrees or so. So this plane here is the plane in which the Earth is going around the Sun. But the plane in which the Moon goes around the Earth is 5 degrees tilted, which means over on the right-hand side, you can see there's a new Moon. The Moon is roughly between the Earth and the Sun, but because it's on a tilted orbit, its shadow actually misses the Earth. The shadow goes too high, and we don't get an eclipse. And on this side, the new Moon, again, the Moon is between the Earth and the Sun, but because of the tilt of the orbit, the shadow misses the Earth. It actually goes, if you like, south of the South Pole. Only when we're in this situation here, these particular points where the Moon crosses this orbit, the plane of the orbit of the Earth around the Sun, these points are called nodes. This is important for the concept of eclipses. So when we get a new Moon that occurs at a node, when it's in the same plane as the Earth goes around the Sun, then we get a very nice alignment of the Earth and the Moon and the Sun, and then we can have an eclipse. These particular points, these nodes, if you draw a line between them, not surprisingly, that is occasionally called the line of nodes. If that line of nodes points towards the Sun, if a new Moon occurs when the nodes are pointing towards the Sun, then we get the possibility of an eclipse. So we can still ask ourselves, okay, we can see why we don't get one every month, but how often do we get this situation where the Moon is in the right position in its orbit just when there's a node, i.e. when the Moon crosses the plane of the Earth's orbit to give us an eclipse? How often does this occur compared to that? And the answer is, this is relatively rare, which is why we don't get eclipses more often than about once every year or two. Somewhere on the surface of the Earth, there will be an eclipse of the Sun once every year, once every 18 months, or something like that. Unfortunately, not in any given place, but somewhere on the Earth there will be an eclipse. So we can ask, well, how long does it happen? How long does it take before the moon's in the right position for an eclipse? We have to ask how long a month is. And that's not as simple as you might think, because we can ask how long does it take a new moon to go back to a new moon again if we follow the phases of the moon from new through first quarter, through a full moon, last quarter, back to new again. How long does it take to go from new moon to new moon? That takes approximately 29.5 days. Fine. But we can also ask, well, how long does it take if the moon is at one of these nodes where it's crossing the plane of the Earth's orbit? How long before it's back to that same node again? That's a different length of time. That particular month is called a draconic month, named after dragons because it's thought that during an eclipse, a dragon is eating the sun. So to go from one node back to the same node again is a different length of time, 27.2 days. So if we want a new moon to go back to a new moon and back to a node, we can't just wait 27 days later because it's not new moon. We can't wait 29.5 days later because it's no longer at a node. How long before they're back in sync again if we start with them in sync? Before I say that, there's one third month that's important, and that is the moon goes around the Earth in an elliptical orbit, sometimes close, sometimes further away. Remember, that makes a difference as to whether we get a total eclipse, a short eclipse, a long eclipse, or possibly an annular eclipse. And that particular month, it's got a funny name, but it's called the anomalistic month, and it's perigee, means the closest to the Earth. Peri, close, G, Earth. Perigee to perigee. How long does it take if the moon is at its closest to the Earth? How long before it's back again at its closest point to the Earth? And the answer is 27.5 days. All of these numbers are different. I'm not going to go through the maths, but perhaps you can appreciate it takes a while, takes quite a few months until these are all back in sync again, because 29.5 and 27.2, they don't divide into each other in any easy way. Somebody has worked out the maths. In fact, the Babylonians worked out the maths thousands of years ago. And it turns out that there is a relationship between them. We're not going to worry about how they figured this out, but it just so happens that that many months of new moon to new moon happens to be 6,585 and a third of a day. So what? Well, it just so happens that that many months of node to node, draconic month, is equal to 6,585 and a third days. So in other words, they do synchronize, but you have to wait quite a few months, in other words, quite a few years, for an eclipse to come back again. Now, 6585, I'm not going to say that number over and over again. Only two things are important here. It's a big number of days. It's about 18 years, so I'm just going to call it 18 years from now on. And it's not quite a whole number of days. There's a 1/3 of a day left over at the end. When we think about, is it going to be at its closest to the Earth or at its furthest from the Earth, if we look at the other months, it almost synchronizes with that as well. A whole number of this month, which is at its closest to Earth, back to the same point again, is 6585, and not a third of a day, but half a day. It's a few hours out after 18 years, and we'll see the effect of that shortly. But because this 18-year period is so important for eclipses, the Babylonians and other civilizations worked out with their lunar calendars every 18 years, if we see an eclipse on one day, that eclipse will reoccur 18 years later. They figured that out from just working out the maths. And that particular period is called a Saros cycle, or a Saros period. It's basically how long before the moon's orbits, the moon's months, are back in sync with each other. So two eclipses separated by this particular period of 18.1 years are very similar. An eclipse that occurs on one day, 18.1 years later, a very similar eclipse will occur again, 6,585 days later. So we're not going to go through all of them, but here's a few of the total eclipses that have occurred in the last quarter century or so. One that was visible from the UK, in principle. It was cloudy, but some people saw it. The last eclipse visible from the UK as a total eclipse was 1999. 18.1 years later, there was another eclipse which occurred as part of that particular Saros cycle. And similarly, there was an eclipse in 2006. This is the one I'm going to tell you about, the one I saw 20 years ago. That particular eclipse in 2006, again, repeated 18 years later. It doesn't mean you have to wait 18 years to see any eclipse. Eclipses will happen at different times, but they will be on cycles, and any given eclipse will repeat 18 years later. There are a number of them happening at any given time, a number of these so-called Saros cycles. Coming back to this idea of the moon's orbit being elliptical, to get an eclipse, we need the moon on the line between the sun and the earth. So if we imagine, just as a cartoon, it's not necessarily accurate, but let's just imagine that we've got an elliptical orbit for the moon, exaggerated a little bit for the sakes of clarity. The closest point to the Earth is called perigee. The furthest point from the Earth is called apogee. Remember, this determines how big the moon appears in the sky and hence how long it takes to cover the sun, or whether it covers the sun at all. So if we imagine we've got the moon somewhere on an orbit like that, on the Sun-Earth line, and there's an eclipse, 18 years later, the moon will again be on the line between the Earth and the sun. But the elliptical orbit of the moon will have changed slightly. 18 years later, it won't be in quite the same position. So if the moon is on the line between the sun and the Earth, it'll be a little bit closer to the Earth. And 18 years later, it'll be again on the line between the sun and the Earth, but it'll be a little bit closer to the Earth, which means the size of the moon in the sky, 18 years later, 18 years later, 18 years later, the moon will be a different size. So you'll get virtually the same eclipse, but the moon will be a different size, which means the eclipse will last a different length of time as the moon moves. If we follow that in terms of actual dates, I've picked a particular cycle of solar eclipses, one that started in 1988. The size of the moon compared to the size of the sun, 1.05, means the moon is about 5% bigger than the sun. So it covers the sun quite easily, and an eclipse lasts for nearly 4 minutes. And that's seen from, in this particular case, it was seen from somewhere in Asia. Why am I pointing out where it was seen? Remember, as the moon goes around the Earth, of course, is spinning once a day, and an eclipse will occur 18.1 years later, 6585 days, and a third of a day. Remember that third of a day that was left over from the 6585? That means when the eclipse comes back again, 1/3 of a day, the Earth will have rotated 1/3 of a day. The shadow will now land on a different part of the Earth. Instead of landing in Asia, 18 years later, that particular eclipse in 2006 landed in Africa, or roughly speaking, Europe and Africa. And if we go to the next Saros cycle, 18 years later, the Earth will have rotated a whole number of times, and a third of a day, it will no longer be in Africa. Now the eclipse will be in the Americas. So you can see eclipses get thrown all the way around the world, partly because this Saros cycle is a third of a day beyond an integer number of days. So this cycle of you'll get an eclipse in Asia, then you'll get an eclipse in Africa, then you'll get an eclipse in the Americas. If we were to go on 18 years at a time, it repeats Asia, and then Africa, and then Americas, and then back to Asia. Notice that the distance to the moon is changing because the size of the moon in the sky is ever so slightly different. 18 years later, it's slightly bigger. 18 years later, slightly bigger. Because it's getting slightly bigger each time we watch these eclipses, the length of the eclipse is getting a few seconds longer each time. Eventually, we'll get to a maximum of about 7 minutes or so, and then they'll start decreasing again. And then if you go centuries into the future, they'll start increasing again. So we can see this cycle, we can see this pattern, and now we know why it is that different parts of the world get these eclipses. It's because of this 1/3 of a rotation. If you go 3 Saros cycles, you're back to square one. That doesn't mean the eclipse is in exactly the same point on the Earth, but it's in the same region of the Earth. This slide was originally intended to be eclipses that are coming up soon. But I wrote this a few years ago and I've never really got round to updating it. So actually this is a little out of date because it talks about eclipses in the last few years. But of course, what interests us is not necessarily the last eclipse, but the next one. 2026, August the 12th. If that rings a bell, that's because it's today. The size of the moon compared to the size of the sun, the moon will be about 4% bigger than the sun. And so the eclipse, if you were to stand in the moon's shadow and watch to totality, the length of totality would be about 2 minutes or so. Not particularly long as eclipses go. And of course, this one is visible from Western Europe. A number of different Saros cycles are in operation here, so they are scattered all over the world. And there's another one coming up, if you're interested, in 2027. Another one that will be visible. Spain is getting a double whammy. Spain are getting this one today, this afternoon. It's clipping the top edge of Spain, and the southern edge of Spain is being clipped by another eclipse in 2027. But look, the moon will be a lot closer. It'll be 8% bigger than the sun, which means totality will last for a whopping 6.5 minutes. And if that doesn't sound like much, when you're experiencing totality, anything more than a few minutes is absolutely fantastic. This gives you an idea of where the shadow of the moon has hit the Earth over the last, over the last 25 years or so. These are eclipse tracks for totality. I'm not plotting annular eclipses here, only total eclipses. The tracks look a bit odd sometimes. That's because, remember, we're looking at a shadow that's falling on a spherical object, and that object is also spinning as well as the moon moving. So the track of the shadow sometimes looks a bit odd when you project it in the standard Mercator projection for the Earth. So America have had 2 eclipses. Some lucky town in America actually had 2 eclipses just a few years apart, where they could go into their back garden and see a total eclipse just a couple of years apart. This is what's happening between 2020 and 2040. I'm now plotting total eclipses in blue and annular eclipses in red. You can see there's a mixture of the two because it's a question of where the moon is in its orbit. This blue one at the top coming down from the middle and coming down and missing the UK and just clipping Spain, that's the one that we are going to experience hopefully this evening. If you went to Greenland, or if you took a boat out into the middle of the Atlantic, or if you fly to northern Spain, you'll be able to see totality. If you stay in England, the track unfortunately just misses England, and so we don't get a full total eclipse of the sun. Only about 90% or so of the sun is going to be eclipsed as seen from the UK. There's another eclipse coming up next year, that's this blue one below it, which clips southern Spain and northern Africa. You might ask, well, okay, there's a few eclipse tracks there over a period of a couple of decades or so, but if I live in a particular point, if I live in Liverpool or if I live in Manchester, how long do I have to wait for an eclipse to come to me rather than me fly halfway around the world in order to see totality? Well, you can get an idea simply by plotting eclipse tracks for not a couple of decades. If you plot eclipse tracks for 1,000 years, it looks like pretty much every part of the world is covered. In other words, everybody gets an eclipse at least once every 1,000 years, regardless of where you are. Unless you happen to be this little bit of green there. That's Northern Ireland. As far as I can tell, Northern Ireland have not had an eclipse for 1,000 years. This is not the future. This is the last 1,000 years of eclipses. And I believe there are little pockets of Europe and a little pocket of Northern Ireland that don't seem to have had a total eclipse for 1,000 years. But most other people are relatively close to an eclipse track. As long as you live for another 500 or 1,000 years, you're probably going to be okay. So for the youngsters in the audience, you're maybe safe. Others, maybe not. It's very rare that we get eclipse tracks crossing within a few years of each other, but it did actually happen in England. Again, I don't think any of you remember this, but back in 1715, there was an eclipse track where you can see the shadow of the moon, relatively large compared to England. It looks small on a world map, but the shadow of the moon can be relatively large. This was predicted by Edmund Halley. And not that many years later, another eclipse came across and went across the Midlands and the southeast. So again, some lucky people in the middle of the country actually got 2 eclipses a decade or so apart. What they made of it at the time in the 1700s, difficult to tell because, of course, we didn't really understand all of the dynamics of the sun. We understood the motion of the Earth and the motion of the moon and how eclipses occurred, but we didn't understand all of the physics of how the sun works that we understand today. I have a few friends who are also interested in astronomy, and given that I read about total eclipses when I was probably about your age, fairly young, I thought, wouldn't it be great to see a total eclipse of the sun? And when we heard that there was one coming in the United Kingdom in 1999, we thought, great, let's all go to Cornwall and see it. But yeah, it was cloudy for us, and we don't talk about that. So having witnessed it went dark and the birds started getting confused as to whether they should be roosting or not, etc., experiencing a total eclipse is one thing, but we wanted to actually see it, and the clouds wouldn't play ball at the time. So my friends and I decided that we would go and see another eclipse, and we would go somewhere where there was no chance of cloud. So a few years later, in 2006, there was this opportunity. Here's the eclipse track, starting in the Atlantic, going across Africa, across a little bit of the Mediterranean, through Turkey, and then through a few countries that I probably can't pronounce properly. So that was a possibility. And the question is, where's the cloud likely to be? And we looked and thought, okay, it's cloudy in England, but that's way off the eclipse track. What about Turkey? Unfortunately, that's likely to be cloudy as well. So my friends and I said, well, if we're going to go somewhere to see an eclipse, let's go somewhere where we are pretty much guaranteed not to have cloud. So we thought, Sahara Desert. Surely they're not going to have clouds in the middle of the Sahara Desert. So it sounds a bit extreme, but we decided to go with that. That's a real satellite picture of the eclipse halfway through. So this is a satellite picture, of course, of Africa, and there's the shadow of the moon as it crosses the Sahara on its way towards the Mediterranean and Turkey. It takes quite a few hours for the shadow to go across the Earth. There's a time lapse of about a quarter of a day, where the shadow starts down here in the Atlantic and goes across Africa and then across Turkey and then over to sunset. So it's clearly on a loop, just so you can get an idea of what it looks like. There's the shadow of the moon racing across Africa. And it does race. It takes a few hours, but it's going supersonic. The shadow on the Earth is supersonic at ground level. So we thought, okay, let's try and do this then. Where do we want to be? We want to be somewhere in the Sahara. Well, what about Libya? That might sound bad, but at the time we were relatively friendly with Colonel Gaddafi, so we thought, yeah, this could work. And an organization that arranges eclipse trips basically said, well, we can hire a cruise ship and lots of people from the UK and elsewhere can fly to Crete, pick up a cruise ship, and then the cruise ship will dock at Benghazi and then take you into the desert to see an eclipse. So I ended up on a cruise ship with 800 other astronomers. It was a real geek fest, but very much an interesting experience. So let's have a look a little bit closer at what's going on there. Yes, there's quite likely to be cloud over the Mediterranean, but cloud over the Sahara? Nope, generally speaking, it's clear. There's the eclipse track. The cruise ship went to Benghazi. Let's blow that up a little bit again. There's Benghazi. There's the eclipse track. Let's dim that down so we can see it a little bit better. There's the center line of the track. That's where you want to be, within a few miles of the center line. So the ship docked at Benghazi, and very early the next morning, we got up and a whole load of coaches took us down into the desert. And the only road through the desert is that one, which meant everybody wanted to be inside that red circle. So it's great that you know exactly where and when an eclipse is going to be, so that you know where and when you need to be there. But it also means so does everybody else. And so quite a few thousand people in this area thought that's where we want to be. Some people decided to go with just that little clip of Egypt. Other people tried Turkey, where there was some cloud. But we figured this is the place to be. And that is my friends and I. There's me in the middle and a couple of my friends and a few thousand other people who turned up at this particular location in time for the solar eclipse. Being British, we took umbrellas with us. Obviously more as a parasol than anything else. and not so much a parasol for us, more of a parasol to keep our cameras from melting, because it was relatively warm. It wasn't unbearable. It was probably cooler than it is today outside. But yes, it was certainly 30 degrees plus in the middle of the desert there. You can see not an awful lot of shade from trees in this particular part of the Sahara. But setting up there, not a problem in terms of elbow room. Yes, thousands of people. You can see lots of coaches there bringing people from all over. But the Sahara is big enough that you can just spread yourselves out and cover whatever distance you like. I took some video, but I'm going to show you some stills because it's possibly it's boring to show you a 2-hour video of the moon slowly crossing the sun. The moon moves its own diameter in about an hour. That's a useful rule of thumb. Hence, an eclipse lasts about 2 hours in total, from the initial little nick of the moon taking out part of the sun to all the way onto the other side. No sunspots visible. The sun wasn't very active at the time. And of course, we were using our eclipse glasses to look at the sun. And in this particular case, I had something similar to these on the front of the camera to make sure the camera didn't get completely overexposed. So we were there in good time and we started photographing minute by minute. I had the camera pointing in the right direction. I had a remote release and I was just taking pictures every few minutes to capture the partial phase as the moon moved in front of the sun. And I must admit, I got a little bit emotional when this started to get even closer and even closer and even closer. Because I had been waiting 40 years to see this. I knew about solar eclipses when I was a lad, and it was only 40 years later I got to see it. And I knew I was standing at just the right place, at just the right time, for the moon to precisely cover the sun. This calculation had probably been done 100 years earlier, and yet to within a second, we knew exactly when it was going to happen, and we knew almost to within a few meters where you would have to stand, give or take half a mile or so, to experience the eclipse of the sun. This, by the way, if I just slowly pause here, that is roughly speaking the amount that we're going to see this evening. In other words, 90% of the sun is covered, a crescent of sun is still showing through. But when you're in the line of totality, you know that that's not the end of the show, that's only the beginning. Because over the next few minutes, the crescent gets smaller and thinner and thinner, and you realize this is going to be amazing. Totality finally reaches when the last bit of the sun is just peeking through a couple of valleys on the surface of the moon. You get this diamond ring effect. You might also notice, if I blow it up a little bit, there's actually structure starting to show on the edge of the sun. Just as the last bit of light goes from the sun, you can start to see these so-called prominences, these huge tongues of hydrogen that are being thrown off from the surface of the sun. Unfortunately, only visible during totality, not during a partial phase. Totality itself, for us, lasted 4 minutes. So 2 minutes after it started, we got beautiful views of the corona of the sun. More of that in just a moment. And 2 minutes after that, we get the final diamond ring where the first little bit of sunlight starts to peek through the valleys of the moon, and you get the diamond ring for a second time. And again, other structures like prominences visible on the edge of the moon. In order to photograph the corona, well, a very short exposure shows you the inner edge of the corona and these prominences, these pink. They look pink because hydrogen glows reddish when it's excited. And so this hydrogen gas is showing up as red or pink. Very short exposure shows some of the structure, but I wasn't sure how long to expose for to get all of the beautiful structure of the corona. So I took a whole load of images of different exposures. 1/1000th of a second, 1/250th. We can now start to see more structure in the corona. Perhaps you can start to see these brushes. This is the north and south magnetic pole of the sun. We can start to see the magnetic field of the sun, something you can't otherwise visualize. Longer exposures start to show more detail, but clearly I'm now overexposing the inner part of the corona. And when I went up to a quarter second, that's 1,000 times longer than the exposure needed to get the inner corona. I figured that was all I needed. But the question is, can you combine all of these images together to give you a nice picture of the sun? And after I got home, I did that and put them together so that you can then see the beautiful structure of the corona, the polar brushes, the North Pole and the South Pole, plus these streamers that are coming off the equatorial regions of the sun. A truly beautiful sight. And it is difficult to really sum up in any sort of words what it is actually like to stand there and just gawp at this. Because during totality, no need for eclipse glasses. You can stare at this, you can use binoculars to see structures on the edge of the sun, and that's why 4 minutes might sound very little, and of course it goes very quickly if you've been waiting for 40 years and then it's all over in 4 minutes, but you try and make the most of it whilst you're there. I enhanced the image to try and show more structure. There's actually a lot of structure in the corona of the sun. Again, we can start to see some of the magnetic fields actually looping around these prominences, these large tongues of hydrogen coming off the surface of the sun there. You often get the question, does it actually really go dark? Well, it won't go dark for us this evening because only 90% of the sun is going to be blocked. And if you leave yourself with 10% of the sun, it's still a bright sunny day. But if you're in totality, we had a video running which shows you just how much the light falls over a matter of 1 or 2 minutes. As you go into totality, yes, the light virtually goes completely. The horizon still stays orangey, a bit like twilight, because although you're standing in the shadow of the moon, somebody 20 or 30 or 40 miles away is still getting sunshine, because the size of the moon's shadow is only finite and is measured in miles, not thousands of miles. Therefore, somebody is still in sunlight, even though you are in the shadow of the moon. So yeah, these were stills taken from a video. So we were taking our own images, one of my friends sitting down there with the camera, and again, we're firing away, taking stills and also having videos run. But this was just a camera set to one side just to film us, so that you could get an idea of the experience of actually observing a total eclipse. And I'll show you not the entire 4 minutes, because that's too boring. I'll just show you about a minute of what it's like when you go into totality. And before I show this video, a warning. This video contains Americans. And Americans can get very loud. Why they insist on whistling and whooping, I don't know, but the sun is still visible, so we're still using our eclipse glasses. People are starting to get excited. We can see the shadow of the moon approaching. Some people are bouncing up and down. I'm being very reserved on the right-hand side there. You can see the light failing. We're about to go into the diamond ring. And now we're experiencing totality, so it's perfectly safe to use binoculars to look at the sun for the next 3.5 minutes or thereabouts. So we were continually taking pictures, but generally speaking, trying to experience the environment, seeing the sun, looking around, seeing the planets In the case of the UK, it's interesting to see what the wildlife was doing when the light failed. In the case of the Sahara, not an awful lot of wildlife, maybe a few lizards on the sand, but apart from that, very little else. So going to Africa to see an eclipse, there's lots of reasons why you might want to go to Africa. I love taking wildlife photos, for instance. But the idea of seeing an eclipse of the sun, well, that just overshadowed it completely, if you'll excuse the pun. This is one of the few times that I use the word awesome. I know Americans overuse that word way too much, but the sight of a solar eclipse, the sight of the corona of the sun, is absolutely awe-inspiring in the true sense of the word. So we're going to get a partial eclipse this evening, but if you ever get the chance of seeing a total eclipse, grab the opportunity whenever you can. Put it on your bucket list and see if you can tick it off. So this is what's happening this evening. The path of totality coming down from Greenland, missing England. Oh, if only it was a little bit earlier. The Earth's rotation would have meant that England was over here. That would have been fantastic, but unfortunately, no luck. The path of totality is going way down the Atlantic, and then it's going to go over, over Bilbao and across Spain, and just miss Barcelona and exit at Valencia there, and I think just clipping the Borealis at sunset. These lines tell you what it's going to be like. So we are somewhere around the middle there. So we're somewhere between 90 and 95% of the sun is going to be covered, about 92% for us. Pretty much regardless of whether you're Liverpool or Manchester, it's pretty much the same thing. This is a little app you can get on your phone designed to tell you what's in the sky. I just set it up for today, Wednesday, August the 12th, and here it is at 6 o'clock. And there's the moon not yet covering the sun. And I ran it forward for 2 hours. And you can see you're going to cover the sun. And then something like 2 hours later, the moon has gone past the sun. Let me just stop it midway. So this is approximately 1913. Doesn't really matter to within a minute or two. But for people in the northwest of England, a few minutes after 7 o'clock is when you get maximum eclipse. And then you can see something like 10% of the sun is still visible. And again, a slightly different way of looking at it. This was a web page that shows you what you can expect. This particular one had a timeline which gave you the time points for when it first enters and clips the sun and when it finishes. It also tells you where to look. Basically, it is almost due west, give or take. It's due west. And the sun is between 10 and 20 degrees altitude. 20 degrees when the eclipse starts, and of course the sun is going down at 7 o'clock, heading towards sunset, and so the sun will only be about 10 degrees above the horizon by the time the eclipse finishes. So ideally, you want to find yourself a western horizon where you haven't got too many trees in the way so that you've got a reasonably clear view down to the horizon. If we run this particular animation, it starts at about 6 o'clock, just after 6 o'clock, and then the moon covers the sun. And the mid-eclipse, again, for us, is around about 10 minutes past 7 BST. And then for the next hour or so, the moon will continue and eventually completely uncover the sun as of 8 o'clock or thereabouts. All of these times, of course, are BST rather than universal time. So again, that's what the mid-eclipse should look like. So if you want to watch the whole thing, by all means do. It'll take 2 hours. Bring snacks, because it does take a while. But if you wanted to just catch it at its best, try and get out there before 7 o'clock, and then you'll see it as this hopefully beautiful crescent sun, which we do not often get to see from the United Kingdom. The last total eclipse was 1999. The next total eclipse, I'm afraid it's another 65 years. So again, the youngsters might be just about okay with that. Most of the rest of us are thinking, well, it's not going to happen on UK soil again. So I hope the skies are clear for you this evening. It's looking good so far. Obviously, it's going to be a very hot day, so maybe that means relatively clear skies. It might be that we have a little bit of thin cloud. That shouldn't necessarily spoil your view too much, as long as you can still get that view of the sun. So if you ever get a chance, put it on your bucket list. A total eclipse of the sun is absolutely fantastic, and I think I can honestly say it was one of the most amazing experiences of my 70-ish year life to date. Maybe I'll see another one, but so far that was definitely one of the highlights. So hopefully clear skies this evening, and we'll sort out some eclipse glasses in a little while. Thank you all very much.